Section 6.2, Example 5 on page 435, we have another way to simplify a radical expression is to rationalize the denominator. You rewrite the expression so that there are no radicals in any denominator and no denominator in any radical. So for example, we have 1 over the square root of 2. We can't have a square root on the bottom of a fraction. So to fix this, we're going to multiply by whatever's missing to make that a perfect square. So square root of 2, if we wanted a perfect square, we would need 2 2's. So we're going to multiply by what's missing, which is another 2. But it needs to be under the radical. Whatever we multiply the bottom by, we have to multiply the top by, because now we're just multiplying by 1. So we're not actually changing the expression. When we multiply fractions, we multiply straight across. 1 times the square root of 2 is the square root of 2. Square root of 2 times the square root of 2 is the same as saying the square root of 2 squared, because we can combine these two radicals, and the square root of 2 squared is just 2. Example 5 says, what is the simplest form of the cube root of 5x squared divided by 12y squared z? The first thing we're going to look at is whether we can simplify the fraction inside. We can't simplify 5 over 12, and we can't simplify x squared over y squared times z. So we're going to go ahead and split this into two separate radicals. So cube root of 5x squared on top, and the cube root of 12y squared z on the bottom. Now, since we're looking at a cube root, we're looking for 3 of a kind. So to rationalize the denominator, we need to have 3 of a kind of everything that shows up in our denominator. You want to look at the prime factorization of any number you have. So since we have 12, I did a little factor tree. 3 times 4 gives us 12, 3 is prime, and 4 can become 2 times 2. So the prime factorization of 12 is 2 times 2 times 3, or 2 squared times 3. So here, instead of 12, we have 2 squared times 3. I left the y squared and the z the way they were. Notice none of these have 3 of a kind. We have 2 2's and 2 y's, but only 1 3 and 1 z. So to rationalize this, we need to create a cube root of whatever's missing. So right now we have 2 2's, but I need 3, so I'm going to include 1 2. We have 1 3, but we need 3, so I need 2 more 3's, which would be 3 squared. We have 2 y's, but we need 3, so we're going to include 1 y. And we have 1 z, but we need 3, so we're going to include 2 z's, which is z squared. Whatever I multiply on the bottom, I have to multiply on the top as well, because we're really just multiplying by 1. Now we can multiply straight across. When we multiply straight across, we can combine these two cube roots into one cube root, since they're both cube roots. We have 5 times 2 is 10, times 3 squared, which is 9. So 10 times 9 gives us 90. We have an x squared, we have a y, and a z squared. So that becomes our new numerator. Keep in mind that we already know 90 doesn't have any perfect cubes in it because it's made up of 5, 2, and 3 squared, none of which are perfect cubes. On the denominator, we have 2 squared times 2 gives us 2 cubed, 3 times 3 squared gives us 3 cubed, y squared times y gives us y cubed, and z times z squared gives us z cubed, which we did on purpose. We wanted these to all be cubes. So now we have a whole bunch of perfect cubes in the denominator under a cube root, so we can take them all out and get 2 times 3 times y times z. Remember, we do not need absolute value bars when we have an odd index, so we're left with just 2 times 3 is 6, and we bring down our yz. The numerator stays the way it is, again, because there were no perfect cubes in it. So our final answer is going to be the cube root of 90x squared y z squared over 6yz. And this was actually a multiple choice problem in the book, so the correct multiple choice option would have been A, as you can see on the next few slides. Now I would like you to try to rationalize the denominator of number 9, the square root of 3xy squared divided by the square root of 5xy cubed.